All right, so in this video, we're going to talk about triple integrals in cylindrical and spherical coordinates. Now, the triple integral setup here, we're going to be our triple integral over bound closed solid region T. And we've got our function now. If we're going to be in cylindrical coordinates, our function is going to be dependent upon r, theta, and z. So this one would be our cylindrical setup right here. And this is where dv would be our r, dz, dr, d theta. Back from polar, you had that additional r in there. I mentioned that was our distortion factor that we'll talk about a little bit later when we get into changes of variable. But right now, the dv, just remember, is going to be the r, and then we followed up with dz, dr, d theta. We've talked about how the combination of dr, d theta in that order generally will lead us toward the desired result due to the fact theta would be our constants. So this is going to be our setup here for cylindrical coordinates. Now the problem we're going to look at is going to be to compute the volume bounded above and below by this sphere and inside this cylinder. So what we're dealing with is something that looks like this. Not that the picture is very necessary, but here's our sphere. We've got our cylinder looking like this. We know that the radius is going to be 3 here, the radius is going to be 2, so we know that the cylinder is inside that. And we want to be bounded above and below by the sphere, and then we're inside the cylinder. So we're going to be looking at something like this. Again, not that the picture is incredibly important in R3 right now, but just to give you a better idea of what it is we're computing. Okay, so to do this, we're going to have our triple integral. And since it's volume, I'm not going to have a function here. I'm just going to have the dv. So I'm going to put in the r dz dr d theta. So r dz dr d theta. And so if we're going to go in this order, then the z is going to need to come first. So if I take this thing and I solve it for z, so if I take this thing here and I solve it for z, that's going to give me a z equals plus or minus square root 9 minus x squared minus y squared. Now, I can't just take this thing right here and drop it in there and there. I know that because, remember, we're only dependent upon r, theta, and z. We can't have x's and y's. But conveniently, we know that x squared plus y squared is r squared. So if I factor out the negative and replace the x squared plus y squared with r squared, now my z is a function of r. So top and bottom for that, we would have z equals the positive 9 minus r squared, and then z equals the negative root 9 minus r squared right there. Okay, so the moment, and I've said this before, the moment you get this first one done, then everything drops back down into R2. So if we go back and look into R2, what we're going to be looking at is I take this and I drop this down into projection in R2. That's just going to be our circle centered at 0, 0 with a radius of 2. So we've got a circle centered at 0, 0 with a radius of 2. If I want to go ahead and sketch that out, you can see that my r value would range from 0 to 2, and then my theta would go from 0 to 2 pi. So 0 to 2, and then 0 to 2 pi takes us all the way around. So there would be your setup in cylindrical coordinates for this particular problem. Now, remember, the whole idea of these multiple coordinate systems is to make our lives easier, and in this case it certainly did, without having to mess with a bunch of these x's and y's that were unnecessary. Now, for this particular one, and I'm always a little bit hesitant to push symmetry too much when it comes to higher dimensions, because even though it might be symmetric, maybe in R2, we don't necessarily know sometimes what's going on in R3. But in this case, we do, and you can clearly see symmetry would be a wonderful way to make this problem even easier. So I'm going to go ahead and run through two parts of the symmetry here that could really help us out some when evaluating. So let me go ahead and make this a little smaller and move it up. Now, the first thing that I want to point out is, obviously, this is the bottom half and this is the top half. So if I change this to a 0, I can put a 2 out in front of here. So let me go ahead and do that. So I'm going to go ahead, change that to a 0. That's still going to be our 9 minus r squared with our square root. This is still going to be a 0 to 2 and a 0 to 2 pi. And that 2 that I'd put out here, that's to accommodate this guy. But we could also go a little bit further if we wanted to. And then this isn't necessary. This is more just to show you how this works. This guy is also symmetric. And so I can't really change the 0 to 2. But I could change from 0 to 2 pi. If I wanted to go, let's say, 0 to pi, I could change that to just the pi, and then I would multiply by another 2 out here. So that would turn into a 4. And that would be a 0 to pi now. And then the rest would still be the same. Now, again, we could go do a variety of different things, but the whole point of me showing you this was just to show you that if you go ahead and use symmetry on individual integrals in a multiple integration setting, that the symmetry would continue to work the same way. You would just need to multiply the outside by whatever was necessary. Okay, so now we'll take a look at spherical coordinates with triple integrals. So we've got our triple integral over bound closed solid region T. We've got our function here now dependent upon rho, phi, and theta, and then our dv. Here, the dv is actually going to be a rho squared sine phi d rho d phi d theta. So rho squared sine phi being the distortion factor, which we'll study a little bit later. But for now, just remember the dv is rho squared sine phi d rho d phi d theta. Generally speaking, we do stick to this form, or this ordering, excuse me, when it comes to setting these things up and evaluating. Again, ending with the constants from the theta. So for this example, we're going to be inside the sphere, we're going to be outside the cone, and we're going to be above the xy plane. So much like the last one, it's not really that important that you see what this looks like in R3, but I do think it's somewhat nice to help for teaching purposes. So here's our sphere, here's our cone, and we are going to be inside the sphere, outside the cone, and above the xy plane. So it looks like we're going to be, let me do this in a different color, we're going to be about right here. So that's going to be the volume that we're computing. So to get things started, we'll go ahead and set up our triple integral. Once again, it's volume, so I'm not going to have this guy. Instead, I'm just going to have the dv, which is going to be the rho squared sine phi d rho d phi d theta. And then I'm just going to go ahead and acknowledge real quick, this is going to be a rho, this is going to be a phi, and this is going to be a theta here and here. All right, so if you'll remember now, the rho was going to be what started here and went out. And so for us, it's going to start here and it's going to go out. You can almost use this edge of the cone to visualize the R a little bit better. And you can see if we start here and we go out, that would be a distance of 3. I know that because the sphere has a radius of 3. So rho is going to be 0 to 3. Now, when it comes to the theta, I'm going to skip the phi for a second. When it comes to the theta, that theta is going to be the around part. So that's going to be the same theta as it was for cylindrical coordinates. So the around would be 0 to 2 pi. So 0 to 2 pi. Now, when it comes to the phi, this is the one that's a little bit harder to see. This is the one that starts here and drops down. So it drops down and around. So we're going to start here and we're going to drop down. But if you think about it, we don't want to start here and drop down because we don't want to include this. We actually only want to include from here to here. So let me mark this. This part right here is going to be part, and this guy right here is going to be the other part. So you can probably already see this green one is going to be pi over 2. So if I start here, I would drop down pi over 2 to end up right there. This one's going to be less than pi over 2. Since we want to keep our integrals with a smaller number on bottom and a bigger number on top, the pi over 2 is going to go up here. So I'm going to go ahead and put the pi over 2 on top. And so then the only other piece we're missing is this. and that would be the smaller angle right here. That's also going to be found when solving for phi in dealing with the intersection of the cone and the sphere. So what I'm going to do is take these equations, convert them into spherical coordinates, where I'm actually able now to solve for phi. So if you'll remember, x squared plus y squared plus z squared, that's going to be your rho squared. And so if rho squared equals 9, then rho would equal 3. I also know that z equals rho cosine phi from earlier. Well, the rho, I'm going to plug the 3 in. I'll have my cosine of phi here, but that's also going to be equal to this guy right here. So what I'm going to have is 3 cosine phi equals the square root of x squared plus y squared. So now I can't quite solve that for phi because I still have x's and y's, but this is where the relationship between x's and y's and phi's and thetas come into play from the previous video. So let me go ahead and shrink this down and move this up a little bit, and I'll bring this guy over. So I'm going to have 3 cosine phi equals, this is going to be a big square root, because remember, x equaled rho sine phi cosine theta. So I'm going to replace that. When I square it, that's going to give me a rho squared sine squared phi cosine squared theta. So the value for x was rho sine phi cosine theta, but it's squared, so all of these are squared, plus, and then my y squared. My y was rho sine phi sine theta, so that's going to be a rho squared sine squared phi and sine squared theta. Now, you've probably simplified enough of these to know by now, you can see we have something in common there and there, rho squared sine squared phi. If I factor that out, that's going to leave me with a cosine squared plus sine squared, which is just going to equal 1. So fortunately, a lot of this stuff goes away. That's just going to leave us with the square root of rho squared sine squared phi. And when I clean that up a little bit, that's going to be a 3 cosine phi. And I can go ahead, and maybe I should have done this from before, but I was too busy talking about what these x's and y's were going to be. Remember, rho is equal to 3, so that's going to be a 9 right there. So maybe I'll even go back and change this to a 9, just so it's a little more consistent with where we're going. So that's going to be a 9. So then I'll have a 3 sine phi. All right, so from there, if I divide by 3, those go away. And if I divide by cosine, then what I end up with is tangent of phi equals 1. Well, that phi now we can clearly see is pi over 4, which does support pretty much what we probably thought going in. This guy right here would be our pi over 4. But the big takeaway from this process is that if we're trying to solve for phi, then it's going to be a matter of converting the stuff from rectangular coordinates into a different coordinate system, allowing us to get phi all by itself. So that angle right there, I'll go ahead and replace with pi over 4. And then there sets our setup for, let me zoom back in so you guys can see that better. There sets our setup for the volume inside the sphere, outside the cone, and yet above the xy plane.